infrastructure that scales. So who am I? I'm Austin Roberts, technical co-founder and CEO of Open Relay, and we operate Rivet.cloud, which is blockchain infrastructure that scales. So what is this doing on the DeFi track? Just a few minutes ago, I heard Patrick from PrimeDAO on the last talk say something to the effect of blockchain infrastructure has never been the problem, and he's right. He's right that the political challenges are very much the weak spot of the blockchain. But from the infrastructure side of the equation, I kind of disagree that all of the infrastructure problems are solved. I'm here to talk about why that is and how we solve those problems at Rivet. So to talk about scaling infrastructure, we have to talk about the rules of scaling infrastructure. So the first thing to understand about scaling infrastructure is that there is nothing new under the sun. People have been scaling systems, computer systems and network systems since the 1970s and even earlier than that. And the techniques of Web 1.0 and 2.0 and earlier, they still work. And if you think you have a new problem, you probably need to learn more about the old problems and figure out which of those old problems your new problem maps onto. Rule number 2 of scaling infrastructure is that bigger is not always better, and in fact, it's very, very seldom better. So given the choice between having more of something and bigger something, you probably want more rather than going bigger. And the reason, there's several reasons for that. One of them is cost. So bigger things get more expensive exponentially, whereas more things get more expensive linearly. So to frame this in terms of infrastructure, if you need a computer that is twice as powerful as the computer that you have right now, you are probably going to be paying more than twice as much money for that twice as powerful computer. If you need another computer that is just as powerful as the one that you have right now, you are going to pay the same amount for that second computer as you paid for the first computer. And that's going to decrease as you get more. You're not going to pay as much for your 100,000th unit as you paid for your first unit because you're taking advantage of economies of scale. Whereas if you need to get one unit that is 100,000 times larger than your first unit, you are going to end up paying way more than 100,000 times more for that much larger unit. So rule number 3 of scaling infrastructure is that things fail. And it's a question of when and how often, not a question of if. Even if you're really good at what you do and you try really hard, things will fail. And to correlate this back to rule number 2, big things fail harder than more things. Big things tend to fail all at once. So if you have one enormous computer that's running your systems and somebody trips over the power cord, that one big thing is gone. If you are running 10 smaller things and somebody trips over the power cord of 1 or even 2, you still got 9 or 8 computers up serving what you need, and you might get slowed down. You might have a partial outage of your service where you're not providing everything, but you're not going to be completely down like you will be if you just have one big system. And people tell me, but blockchains are new and different. No, they're not. Not from an infrastructure scaling perspective. A blockchain network is just a redundant system with many small nodes. So you've got, at Rivet, we mostly work in Ethereum. So you've got these Ethereum nodes all interconnected. And node failures don't disrupt the network as a whole. If this guy loses his internet connection, somebody tripped over the power cord, the network is still resilient. The network is still there. It's still, creating blocks, processing blocks. Now, you will notice that these guys down here are no longer connected to the rest of the network because they were connected to each other and they were connected to this guy, but they weren't connected to anybody who didn't just go down. So, now they are no longer getting updates, but the network as a whole is resilient and will keep operating. And should these guys ever find other peers that are still connected to the network, there is a process for reintegrating them and getting them back up to speed that will happen, wholly automatically. So that's great for the health of the network, but it's not so great for dApps and DeFi projects that need to connect to the network. So dApps connect to a node for data. When whether you're talking about needing somebody's token balance or CryptoKitty status or loans or whatever, you have your users who connect to a dApp. The dApp connects to a node. The node connects to the rest of the network and pulls down the data. That node has limited capacity. It can only handle maybe up to a couple hundred requests per second before it starts to grind to a halt. And it's also a single point of failure. So if this node goes down, then this dApp stops getting this data and this user is sad. And rule number 3 of scaling infrastructure is that things fail. So in this example, some node that's 2 hops away from us just died. So our nodes are no longer connected to the rest of the network, and our dApp stops getting updates. So our dApp is sad and our users are sad because while they're still connected to this node, they no longer have current information. So the solution here, rule number 2, more things. So instead of running 1 node, run 2 nodes. Maybe make sure that they're connected to different peers so that if one of them goes down, they don't both go down. And then you have your dApp route requests to both of them. They go through something called a load balancer, and this may look like it's just one thing, but in reality, load balancers are implemented as multiple things so that they can't go down, unilaterally. And now you're more likely to survive hiccups because if this node goes down, you can still route stuff to this node and vice versa. So there's an exception here because one of your nodes is now serving stale information because it was relying on this guy that's no longer there, and now your dApp is getting inconsistent data because when it makes a request to this node, it gets current information, and when it makes a request to this node, it gets stale information. So for example, if you have just sent DAI from one address to another, if you query this node, it's going to tell you that it's in the new address. If you query this node, it's going to tell you that it's in the old address. So if you've got this dApp that's making requests to both, it might make it look like it exists in both places, or it exists in neither places. So inconsistent data can cause lots of problems for dApps. But it's okay because health checks can solve this. So the load balancer can evaluate whether or not this node is healthy. It can say, oh, you're running behind on information, so I'm no longer going to route requests to you. So generally, you can work around that. Kind of. There's still some other problems that arise that we're not going to go into right now. But this isn't about how to build resilient infrastructure. This is about how to build scaling infrastructure. So now it's time to scale. You've acquired more than just one user, and congratulations, you've got a lot of users. But now, even with 2 nodes behind a load balancer, your nodes can't keep up with the demand of your users. So again, is the solution more things? You just put another node behind your load balancer? Well, there's some problems with that. First of all, more nodes lends to less consistency. So the more nodes you have getting information from different peers at different times, they're going to have an even less consistent view of the world than in the example that I gave earlier. The other consideration is that blockchain nodes spend a lot of effort validating data that they get from peers. One of the neat things about blockchains is that they are a trustless peer-to-peer system. This means when you download data from your peers, you do not trust that it is correct. You take that information and you cryptographically verify it. However, that cryptographic verification process is very computationally intensive. So when you have to scale up the number of peers in order to serve more requests, you also have to scale up that validation process. And all of your nodes are going to be doing the same validation process over and over and over again. The final consideration is that overloaded nodes take longer to validate. So an idle node might be able to process the blocks that it gets from peers in about 80 milliseconds, give you that data very, very quickly. Overloaded nodes that you're hitting with 1,000 requests per second, it might take 5 or 10 seconds to validate a block. in which case the information that those thousands of requests per second are actually getting is very outdated. But there's nothing new under the sun. Databases solved this problem back in the 70s, and their solution is called streaming replication. So in streaming replication, you have multiple copies of your database. One of the servers is in charge of the writes. We call that the write master. And then you have as many read replicas as you need in order to serve your read capacity. The master is unaffected by read workloads. So if you have tons of read operations, so long as this master is big enough, and the master is one that needs to get bigger, or may need to get bigger, not necessarily get more of, that master is unaffected by read workloads. So it doesn't have to get bigger just because you have more reads. The only time it's going to need to get bigger is because you have more writes. And then you can get more read replicas to scale up your capacity. And that makes it easy to achieve high consistency at scale. So we took this principle and we did the same thing to Ethereum nodes. So we have our masters at this layer that are connected to the peer-to-peer network. They do the block validation so that our replicas don't have to. Then we have as many read replicas as we need in order to serve our requests. The masters are unaffected by read workloads. All they do is pull down data from peers and validate it. And then the replicas handle the read workload, making it easy to achieve high consistency at scale. And we also have no single point of failure. The peers can die. We have multiple masters, so they can die. Replicas can die. Any individual server in this equation, and often multiple servers, can die at the same time, and the system just keeps chugging. So the next thing to do if you want to scale your infrastructure is to avoid monoliths. So you want to minimize the functionality of a given service and avoid having single servers with multiple bottlenecks. So you don't want to have high compute and high disk on the same server, because then if you need to scale the compute, you also need to scale the disk along with it, even though the disk may not need to scale at that moment. So if you put the compute on one set of servers and the disk on another set of servers, you can scale them independently without having to raise the cost of scaling both at the same time. The last point here is to take advantage of cloud storage. It's slow compared to local storage or memory storage, but it is dirt cheap. So if you have things that are not particularly performance sensitive, put them in cloud storage and you can get that data stored very cheaply and get it as you need it. So as an example, how did Rivet achieve this? So we started with a monolithic replica that had log data, block data, state data, WebSockets, and we broke it out into several different components. So the WebSockets moved off to their own server. This is compute intensive, but it has no disk whatsoever. We can scale that very quickly and easily. We moved logs to another server that we call Flume. They're indexed. We can query them much more efficiently than a conventional Ethereum node. But that also means that we don't have to have it with everything else. So now we have the state on another server that allows us to get contract data. So what is this Ethereum account's token balance? We can get that from this server. And if we need to scale up our contract state server, we can do that without having to scale up logs. If we need to scale up WebSockets, we can scale that up independently. And then finally, we moved block data off into Amazon S3, where we could store it very cheaply. It's not as fast, but we never need very much of that at a single time. So we can get it, serve it, and we're good to go. So where can you learn more? Find us at our Umbrella booth. We'll be hanging out there. Rivet is open source. You can check us out on GitHub, build it yourself, see how we did all the things that I just talked about. We focused on Ethereum, but these principles are chain agnostic. They don't just apply to Ethereum. You could use them for Bitcoin or any other dApp system. Check out our docs at rivet.cloud/docs. And if you want to sign up for our service, you don't want to manage the infrastructure, you want to count on us to scale it, check out rivet.cloud/signup. Promo code LA2020 will get you 500,000 free requests. And I think I'm out of time. So thank you.